Okay, ladies and gentlemen, welcome back. This is Genetic Drift. We talked about, would you guys like to hear some intro music here? Intro music. Andres Segovia. Ladies and gentlemen, welcome to Genetic Drift. Anyway, sorry about that. Wasn't that pleasant? Sorry. Okay, so genetic drift. We talked about different mechanisms of evolution besides natural selection. We talked about artificial selection, sexual selection, intrasexual selection, intersexual selection, frequency-dependent selection, and I can't remember what else. I think that covers most of it besides natural selection, besides luck. Luck has an effect. Living things that are under natural selection and living things that aren't under natural selection are still subject to gene fluctuations based on luck. If we recall, there are traits for which natural selection works directly, and I'm sorry, this is going to make you seasick. Here we go. So directional selection. Microevolution is the change in gene frequencies in individuals that have those gene frequencies over time. So which we saw in our original picture. There it is, right? We got light and dark. We got light and dark bugs. They're the same species. As long as the environment is dark, then the dark ones have the advantage. We expect the predators to have an easier time hunting the light ones. They eat the light ones, and so on. Yeah. So this gene, whatever genes these individuals have that cause them to be light or dark, are under selection. Yeah. In the same way, if we thought of polar bears, we just passed a polar bear, didn't we? Where's that polar bear? Whiteness of fur in the polar bear confers an advantage over dark fur because that allows stealthy, sneaky polar bears to creep up on whatever it is they're trying to eat, probably seals or sea lions or whatever they're eating, and catch them by surprise more easily if they blend into their surroundings better, yeah? So these genes are under selection, yeah? But humans, for example, have about, it's 17 to 30,000 genes. You would think the number would be known more precisely by now. It's still pretty variable. They probably know it a little better than I know it, I think. But the number is not just a few. There's thousands of genes. So for a few important genes, like the color of your fur, the warmth of your fur, the sharpness of your claws, the craftiness by which you sneak up on your prey, those genes have an influence on whether you survive or not. Other genes are less important for that matter, yeah? So the example I used was free and attached earlobes, and I don't have a picture of free and attached earlobes, but we can pull one up. Google image, good old Google image, my second favorite website. Free and attached earlobes, booyah. Okay, so there it is. You got your earlobes, you got your free earlobes, you got your attached earlobes. There they are. So there's your free earlobe, there's your attached earlobe. Does this matter? This is thought to be, and you better not take it to the bank that it actually is, but this is thought to be genetically inherited. There are genes that influence what kind of earlobes you have, whether you got free ones or attached ones. But having free or attached earlobes is not, I hope you agree, too important to human survival, yeah? Likewise, there are thousands of genes we can expect in polar bears, in little bugs, in butterflies, in whatever, that aren't being selected, even though others are. However, just because a gene is not under natural selection, just because a gene for which there are two variants, we call those variants alleles, we'll learn that term later on, but for any gene for which there are variants, the variants of that gene which don't confer a survival advantage and reproductive advantage are still evolving. They are still fluctuating, but they are fluctuating by luck. Dumb luck makes some genes become more frequent and other genes become less frequent, even though they don't do anything to help that living thing survive. So here is the example. We've got some flowers, they're red and white, and we assume, at least for this situation, that being white or being red, if you're this particular breed of flower, doesn't do anything for you. It doesn't make the bees happier. It doesn't make humans want to plant you more or whatever. Whiteness or redness doesn't do squat. And if that's true, that does not mean that the gene frequencies won't fluctuate, as we saw the gene frequencies of lightness and darkness fluctuate in the bugs, and as we would expect lightness and darkness genes to fluctuate in polar bears. So let's look. If we look at this, we can see that in generation 1, and I'll make it bigger in case that's too small. In generation 1, we have what are called gene frequencies, P and Q. P refers to the number of big letter R's, and we can see that big letter R's cause flowers to be red. The lack of big letter R's cause flowers to be white. Yeah, and we can see if we counted all the little R's, everybody's got 2 of them. That's something we'll learn later. You don't need to worry too much about that. But everybody's got 2 R's. This one's got 2 big ones. This one's got a big one and a little one. This one's got 2 little ones. And because this one doesn't have any big ones, it's white. Because these ones have at least 1 big one or more, they're red. Yeah, so this has to do with dominance and recessive, and you don't need to worry about it, right? Nevertheless, if we counted all the big R's and we counted all the little r's, we'd see that 70% of the R's are big and 30% are little. Why? Because those are our initial conditions, and again, this is a gene that is, at least in the environment that we're considering, not being selected. Yeah? So, and there I said yeah. I say yeah a lot. I just watched that video of myself, and I say yeah a lot. Sorry about that. I'll try to say yeah less, but I'll probably fail at that attempt. Anyway, so if the population of flowers in the particular ecosystem, in the environment that they're in, stays constant, and we expect it to, at least under these sort of hypothetical conditions, then the frequency of big R's and little r's as these little flowers interbreed with each other can change. It changes by, again, by luck. Some of these guys happen to reproduce, some of them don't. Maybe they reproduce because they're better fit for the environment, but they're not better fit for the environment because of redness or whiteness. They're more or less fit for the environment because of genes that we don't know about, that we can't see in this picture, and that we're not considering. Yeah? Nevertheless, the population of these guys is remaining constant, but as we can see, the frequencies of big R's and little r's isn't. Why? Well, because luck. What is our population? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 guys. So the volatility of luck is very high when the population is small. And here we see the frequency of little r's has gone up to 50%. Why? Because luck, because of the luck of the draw, because these things randomly mating with each other or mating with purpose for other reasons than color of flowers result in this frequency just by luck. And if we look at another generation, we can see here that the gene frequency has gone to 100% of big R's. Why? Because big R is better? No, big R is not better. Big R got lucky. Yeah. So this is completely calculatable by mathematical probabilities. Unless a population is infinite in size, frequencies of genes will fluctuate even if natural selection isn't working on them. And so here, I promised you I'd show you a little simulation that I thought would help. This is the simulation. This is a picture from a textbook that I got from the internet somewhere. And we can see, and if we go back here, we can predict what's going to happen in generation 4. Everybody's going to be red. Why? Because there aren't any little r alleles that confer whiteness. So let's look here. We can see that once this is the gene frequencies, 0.5, which is 50%. Oops, excuse me. 0.7, which is 70%, and so on. Sorry, there it is. This is going up to 0.9, down to 0.8, yada, yada, yada. Let's look at the simulation. Where did my simulation go? There it is. Okay, so there is if I clicked on that link that I had in the PowerPoint, and if you click on it, you can come here. Ooh, look, I liked it on Facebook. Anyway, so population size of 50. We're going to run 200 generations. The frequency of one allele is 50%. The frequency of the other allele, well, it's 50%. Yeah, it's got to be. Because we're assuming that there are two alleles, it's worth pointing out now that there can be many alleles, many more than two for any gene, many variants for one particular gene, and we'll talk about that later when we get to genetics. All right, so there's a little go button, go, and we can see what's going on here. Is there a pause button? I don't know if there's a pause button. But what's happening is little lines are going up and down, and they're going up and down in exact opposite. We started with how many little lines? 1, 2, 3, 4, 5 little lines. And how many do we end up with? After 200 generations, we have 2 lines left. What does that mean? Well, that means if this is flower color, this pink one here, can you see the pink one? Right? That means that in the population of 50, the red allele went up for a while up to 80% and then went down to 0, whereas the white allele started at 50, went down to 20% and went up to 100. Yeah, that means the white allele, the red allele was lost. Yeah, and conversely, if we look down here, we can see that the white allele got fixed. Yeah. What if we had another trait like leaf wrinkles? Yeah. How many wrinkles you got on your leaves? If you got a lot of wrinkles, then that's one allele, and if you have a few wrinkles, that's another. Well, maybe that one is blue, and if it's blue, then it goes up for a while, goes down for a while. Yeah. Why? Because luck. As long as we assume that these things aren't being naturally selected for, then they're fluctuating randomly. This program is basically going through generations, keeping the population at 50, doing 200 generations where the individuals that hold the alleles randomly mate, right? There's 50 of them, whatever they are, whether they're flowers or, you know, pterodactyls or polar bears or little bugs. Whatever they are, they have genes that are not being selected and they fluctuate randomly. What if we ran it again at population 50? Well, let's see. Here we go. Isn't this exciting? Go, go. So now the pink, ooh, look, pink got fixed. See, now, instead of the gene being lost, we say it's fixed. That means it went up to 100%. That means the other allele was completely lost. And again, once these alleles are lost, they're not coming back because the allele is gone from the population. And here, only 1 out of the 4 made it so what is happening to diversity in this population? Is it going up or down? Everybody think. And if you thought for a while and you came to a conclusion, you would say that the diversity is going down. In fact, 80% of the genetic diversity has been lost from this population after 200 generations at a population size of 50. Is that clear? I hope it's clear. If it ain't, you can ask me questions during class. Okay, what if we increase the population size? What if we went up to 500? Do we think we'd have more or less genes getting fixed? Well, hopefully you answered fewer genes getting fixed or lost because the effects of luck are reduced when population sizes are greater, yeah? Oh, great, now it's really slow. But look, we can see that the variance in the fluctuation, the tendency to fluctuate, seems a lot more reduced, and things, the tendency toward the initial conditions of 50% is greater. Yeah, that doesn't mean nothing is going to fix or get lost, but the higher the population, the lower the effects of genetic drift. So, look at this. Isn't this exciting? Wow. It's kind of like digital horse racing. I think there was a video game when I was a kid of horse racing. You could bet on little digital horses. You put in a quarter and it was a video game. It was kind of like Pong. It was released at the same time. You'll have to pull that up. You guys have other things to do than have me pull up old video games from the 70s when I was, alive. So you think this blue is going to fix? Doesn't look like it did. Looks like they all made it, yeah? Should we continue? Continue. We'll go for another and see if one of them is going to fix. I'm sort of hoping something does. But, right, we haven't lost any genetic diversity. Some genetic diversity has gotten greatly reduced, but we haven't lost any, and it's been 200 generations. Come on, let's get something to fix. Oh, man. Well, never mind. Okay. So, and notice how slow it's going because computers are slower when there's... Okay. Let's change the population to 10. And we'll press reset. Population is now 10. What's going to happen now? Well, we would expect more to fix. We lost 80% when there were 50 in 200 generations. Boom. Adios. We've lost, after less than 40 generations, we lost all the genetic diversity of this population by luck. There are, right, so hopefully that's interesting, yeah? Okay, so that hopefully gives you the idea. When genes fluctuate randomly, they have ultimately hit a sticky barrier. That is, they go to 100% or to 0%. Does this show you why a bottleneck event removes diversity? Right? Effectively, a bottleneck event is where the population is grossly reduced. Right? And the reason the frequency is lost is because that's what happens. This is like genetic drift in a single generation on steroids, yeah? If the population stays small, the frequency of the little green guys is also likely to disappear, and we are likely to completely lose diversity in this population. Is that good for a species? Certainly not. It makes a species very vulnerable to extinction when conditions change, when a pathogen shows up and there's no genetic diversity, then we don't know if one gets sick, they're all going to get sick, right? If they're genetically identical. Doesn't that seem likely? So cheetahs are an example of a species which has passed through a bottleneck event in the past. And we can infer, right, when we see that species become endangered, even if they make a recovery, we expect there still to be major negative effects, right? Because when the population returns to normal, the diversity is still gone. When that sticky barrier is hit for any gene, those variables are not coming back. What brings diversity back into a population? Well, the two major mechanisms that should hopefully be leaping in your mind are mutation, that should definitely leap in your mind, and hopefully you're also thinking sexual reproduction. When sexual reproduction, you're combining two genomes, you're not making new genes, but you are shuffling the old genes to make new combinations, yeah? But if you don't have any genetic diversity in your population, because there's been a tremendous bottleneck, then sexual reproduction can do very little to allow the species to reinvigorate its diversity, to shuffle its diversity. Because if you don't have any diversity to shuffle, then sexual reproduction as a mechanism of generating diversity doesn't do much, because it doesn't do anything novel. Only mutation can create brand new stuff, yeah? Okay, so likewise, the founder effect, things that are on islands the islands are usually populated by very small populations. That grossly limits the genetic diversity available to those populations. And yet, if we look at adaptive radiation in islands, we can still see that even with a grossly limited gene pool to choose from, you can still get strong speciation. But hopefully I've made it clear what genetic drift is all about. Okay, and sorry that took so long. Have a great day.